If your player script is a wall of if statements, you need a state machine. In the next 15 minutes we build one, clean, reusable, in Godot 4. Idle, run, jump, and attack, with copy-paste ready code you can drop into any project. Quick, honest heads up before we open the editor. This exact state machine pattern, plus 50 other copy-paste snippets for Godot and Unity, lives in my gamedev starter kit. $19, completely optional, and the link is below. That's the whole pitch. Now, let's build a clean state machine in Godot. Let's start with the pain, because you have felt it. Here is how almost everyone writes their first Godot player controller. One giant physics process function, stuffed with flags. Is jumping. Is attacking. Is on floor. Can double jump. And a tangle of if-else branches trying to guess which combination is true right now. It works, for about a week. Then you add a dash. Now every branch needs a not dashing check. Then a wall slide. Then a hurt state where the player can't move. Each new ability multiplies the branches, because every state has to know about every other state. This is the wall of if statements, and it breaks for one simple reason. There is no single answer to the question, what is the player doing right now? The truth is smeared across 10 booleans that can contradict each other. You get bugs where the player is somehow attacking and jumping and idle all at once. A state machine fixes this at the root. Instead of 10 flags, you have exactly one variable, the current state. The player is in idle, or run, or jump, or attack. One at a time. Never two. That single idea removes a whole category of bugs before you write another line. So what is a state machine, really? A finite state machine is just two things. A set of states, and the rules for moving between them. A state is a mode of behavior. Idle is a state. Run is a state. Jump and attack are states. At any moment the player is in exactly one of them, and only that state's code runs. The idle code does not run while you are jumping. That is the whole point, clean separation. The second half is transitions. A transition is a rule that says, from this state, on this condition, go to that state. From idle, press a direction, go to run. From run, press jump, go to jump. From almost anywhere, press the attack button, go to attack. When attack finishes, fall back to idle. Draw those arrows and you have designed your player before touching code. Here is the mental model to hold on to. Each state is a small, self-contained script that knows three things. What to do when you enter it, what to do every frame, and when to hand control to another state. Nothing more. If you want to follow along with the full written code, the complete tutorial is on screen. Every snippet from this video is there to copy. Let's build the foundation now. Everything starts with one tiny base class, the state. This is the contract every state agrees to follow, and it is genuinely this short. At the top, class name state, extends node. Class name means every other script in the project can refer to the type state directly. Extends node means a state is just a node in the scene tree, lightweight, no rendering, no physics of its own. Then 4 empty functions. Enter, called once when the machine switches into this state. Exit, called once when it leaves. Physics update, called every physics frame while this state is active. And handle input, for input events. They are empty on purpose. This base class does nothing by itself, it just defines the shape. Each real state, idle or run or jump, extends state and fills in only the functions it cares about. An idle state might only override enter and physics update. It ignores the rest. One shared line, a reference to the state machine that owns this state. The machine sets that when the game starts, so from inside any state you can call the machine and ask it to transition. That is the entire base class. 4 hooks and 1 reference. Small on purpose, the power comes from how we combine them. Now the brain, the state machine node itself. This is the piece that holds the current state and drives it every frame. Look at the node tree first. Your player is a character body 2D. Under it, a sprite, a collision shape, and a plane node called StateMachine. Under the StateMachine, one child node per state. Idle, run, jump, attack. That's the pattern. States are literally children of the machine, so you can see your whole design in the scene doc. Here is the script. Class name StateMachine, extends node. An exported initial state, so you pick the starting state in the inspector. A current state variable. And a states dictionary, which maps a name like run to the actual state node. In ready, we loop over the children. Every child that is a state gets registered in the dictionary by its name, and gets a reference back to this machine. Then we enter the initial state. Physics process is the whole engine, and it is one line. Call physics update on the current state. Whatever state you are in, only that states per frame code runs. Unhandled input does the same for input events. And the star of the show, transition. You pass a state name, it looks the node up in the dictionary, calls exit on the state you are leaving, swaps current state to the new one, and calls enter. Leave cleanly, arrive cleanly. Every state change in your whole game funnels through this one function. Now the fun part, the actual player states. Each one is a small script that extends state. Watch how focused they are. Idle first. On enter, we stop horizontal movement and play the idle animation. Every frame, we check two things. If the player is not on the floor, transition to jump. If a movement key is pressed, transition to run. That is the entire idle state, it only worries about how to leave itself. Run is just as tight. On enter, play the run animation. Every frame, read the input direction, set the player's velocity, and flip the sprite to face the way you're moving. If the input drops to 0, go back to idle. If the player leaves the floor, go to jump. Notice the run state never thinks about attacking or idling internally, it just knows its own exits. Jump sets an upward velocity on enter, then applies gravity every frame while airborne. The moment the player lands back on the floor, it transitions to idle or run depending on whether a key is held. Attack is the clean one. On enter, play the attack animation and freeze movement. It waits for the animation to finish, then transitions straight back to idle. No flags, no timers scattered across your controller, the state owns its whole life cycle. For small files, and each one is readable on its own. Let's talk about transitions properly, because this is where a state machine earns its keep. A transition is one line, StateMachine, transition, then the name of the state you want. The magic is where those calls live. They live inside the states, not in some central megafunction. Idle decides when to become run. Run decides when to become jump. Each state owns its own exits, so adding a new ability never touches the others. Picture the diagram on screen. Idle connects to run and to jump. Run connects back to idle, and up to jump. Jump lands back into idle or run. An attack sits off to the side, reachable from almost anywhere, and always returning to idle. Those arrows are your design. The code just mirrors them. Want a guard condition? Only allow a transition when something is true, like, you can only enter jump when the player is actually on the floor. That check is a simple if, right before the transition call, inside the state that owns it. No global flags. The condition lives exactly where it's relevant. This is why the pattern scales. 10 states or 50, the rule never changes. One state active at a time, and every change goes through transition. Your controller stays flat and readable no matter how big the game gets. Ready to level up? Once you have a few states, you'll notice some of them share behavior. This is where a hierarchical state machine comes in, and it is a smaller jump than it sounds. Take attack. In a real game, attack is not one thing. It's a light attack, a heavy attack, maybe a 3-hit combo. In a flat machine, that's 3 separate top-level states, all duplicating the same, freeze movement, then return to idle, logic. A hierarchical state machine lets a state contain its own little state machine inside it. So attack becomes a parent state, with its own substates, light, heavy, combo. The parent handles what's common, like blocking movement. The children handle only what differs, like which animation plays and how much damage lands. The beautiful part is that it's the same pattern nested. A substate machine is just a state machine node living under a state, running its children exactly the way the top machine runs the player's states. You already wrote the engine. You're only reusing it one level down. Start flat. Reach for hierarchy only when you feel the duplication, usually in combat, or in complex enemy AI where chase splits into chase near and chase far. Don't build the hierarchy before you need it. But when you do, the upgrade is almost free. And that's a clean, reusable state machine in Godot 4. A tiny state base class, one state machine node, and small focus states for idle, run, jump, and attack. The exact same pattern powers enemy AI, swap the player states for patrol, chase, and flee, and the engine doesn't change at all. Here's your next move. Do not stop while it's fresh. Your next watch is lined up, how to spawn objects in Godot 4, the instancing pattern you'll use to bring those enemies into the world. And the game dev starter kit has this state machine plus 50 more copy-paste snippets. Link below. Subscribe for more Godot builds. Now go delete some if statements. See you in the next one.